Hi, everyone. Welcome to the talk. My name is Qing Zhang, and I'm from eBay structured data team. So in this talk, I will talk about how we use Spark to discover new metadata from eBay listings. And this is a joint work with Ray Li, who's also from structured data. So in this talk, I will first introduce our organization, and then the problem, and the next solution, and the conclusions. So we're from a structured data team, so we're responsible for transforming unstructured listing data to the structured information with semantic meanings. These are the following important domains in our team. So first one is metadata discovery. So what we mean by metadata are basically the important name value pairs on eBay. So for example, brand is an important name, and Apple is a value. So those name value pairs are always used for describing those are important information to describing the listings. So we have this metadata system that's discover and also manage the repository, and so that we can power the eBay website in a lot of important applications. So one application is like in this search page, you can see that on the left-hand side. So these are the filters, and they are all powered by the metadata repositories. So these are the important name value pairs that relate to those recalled the listings. And also, if you want to sell something on eBay, you will also have a lot of interactions with metadata. So these item specifics are also generated and based on our metadata system, and we also provide those recommendations. So the other important domain is listing classification. So we have a lot of classification tasks for listings. So one important task is listing category recommendation. So given a listing, we have this recommendation system automatically recommends the most likely categories for those listings from thousands of categories for user, so that the user can only have to go through maybe 10 most likely categories and to choose from. And we also have other categories, other classification tasks like taxonomy classification. So basically try to assign predefined taxonomies to listings like product types. So the third domain is catalog. So we basically we create, collect, and also manage the catalog system, so that given a listing item, we have the algorithm to map them to the catalog. In this case, this listing item will be mapped to a certain product, and it will enable a lot of important applications, such as the fourth one, so inventory insights. So since we have all the items, certain items mapped to the same product, so we can generate a lot of price-related insights. For example, those are like what's the best-selling products on eBay right now, what's the price range, and also what's we will predict trending price for certain products, and we also identify deals for the product within those products. So as you can see that metadata is the kind of one of the fundamental building blocks for all those applications. So it powers both selling and buying, and it enables a lot of internal applications. So one important task is to discover new metadata from listings. We have millions of new listings every day, so it's very important to keep the repository up to date. And in the past, it's highly rely on human to review the candidates, and it is very challenging, as you can see in this example. So these are all brand candidates, and many of them are not straightforward at all. You have to do a lot of search, and to make things even more complicated, you can see in this. In this example, many terms they actually are brand candidates for a lot of different categories. So the reviewers have to go through every category to make sure that this is a brand for this category. So basically, this brand has product in this category, so which requires even more effort. So therefore, we start thinking about using data-driven approach to discover those new metadata. And in this, in this project, our approach is to mine the item specifics. As you recall, so when user sell something, they will input a lot of item specifics to describe their items, and we also suggest them to suggest certain fields to input. Sometimes they will, of course, they will make a mistake. So if we can basically classify their inputs as valid or invalid, then we're able to discover new metadata directly from their inputs. And we also have the intuition that actually the supply and the demand signals that we collect from buyers and sellers are directly correlated to how valid these item specifics are. For example, so if for the term that has been used for thousands of unique sellers as a brand for this category, then it's very likely that it is a valid brand compared to some brand that's some terms are rarely used. And so also similarly, so if this term has been used, has appeared a lot of times in the titles, it's also a strong indicator. And also we have the data as we've been doing human review for a while. So we have been accumulated those reviewed candidates. So basically there are decisions whether it's approval or rejection or reason of the reason of the rejections. So we can basically utilize those reviewed candidates as training examples. So we have the hypothesis and we also have the data. So we'll basically collect those around 35,000 human reviewed metadata candidates, and we associate the supply and the demand signals with those candidates. So these are the features for those examples. So we did prototyping with Python, and the results shows that those ensemble methods such as random forest has fairly good results, which supports our hypothesis. So we want to move forward to implement them production. So in the past, so one common practice of implement those machine learning applications on production is to basically you train the model offline and you upload your trained model to the production and also write the prediction components on production, partially because so at least for us, so the production environments in the resources are very restricted. So we're not allowed to do a lot of very intense training with a lot of data, and also and also some majority of the applications are not on HDFS, so people tend to apply those machine learning, so just implement on certain clusters and run those predictions on these clusters. But for our projects, so we basically this time our data are all on HDFS. If you still take this route, will involve a lot of file transferring and configurations, and which are very time consuming. So our pipeline will be divided into multiple pieces. And also, it's very hard for machine learning applications. You always have to run the model and to see the predictions and do the error analysis. So it's really important that if you can just develop and test on your local machine or on your development machine. So then we start thinking about Spark. So we've been using Spark for data processing for a little while, and so we found that it's very useful for data transformation, and especially for those tabular structured data. And so we also found that there's MLlib, which covers a lot of commonly used machine learning packages, machine learning algorithms such as regression, classification, clustering, and some important routines like dimension reduction. So we we just found out this probably is it's an ideal tool for us to implement this production application. So, and also one important thing is the MLlib is very well connected with Spark. So basically, if you can run Spark, you can run MLlib, so you don't have to do any like additional configuration or something. And it has very flexible data access. So you can run it on your local machine, and you can access a single file or folder or a lot of different inputs, just one different input formats. So and then we just implement this machine learning system, which is really standard. So it's completely based on MLlib. And so it has three components. The first one is feature generation. So we basically use Spark to pre-process the data to get all the supply and the demand signals, and to output them into the feature vector file. And in the training parts, we just use the MLlib's random forest to do the training. And the good thing is so after the training, the model will be directly saved to the HDFS, and you don't have to transfer it at all. And for the prediction parts, we just read in the new data and load the model and do the predictions. And also the output will also be on HDFS. So this whole project is completely on HDFS and without any file transferring needed. And so here for machine learning part, we found it's really useful to use the pipeline mechanism. So basically, you can just put you chain your data and the steps into a pipeline, and then you can define your, also here the RF is random forest. I didn't show it right here. So, and also you define your own evaluator, and then you define your own parameter grid as well, and then you put all those information into cross validator to let it run and to select the best model. So this is essentially the training part of the project. So you can see that it is very straightforward. And we did some evaluations. And you can see that there are a little bit performance variations across different implementations and settings. So, but these variations are acceptable, and we found that it's like it's hard to decide like how many executors we want. It seems that they're not completely correlated with the performance. So right now we still have limited understanding of the implementation of the MLlib. So still not very sure about this one. And also we found that Python has slightly better performance than the MLlib. So we also, in the future, we still also need to find out the implementation details. And also this is the latest run on production, and you can see that the overall the speed the time that it requires is really small. So basically, so for feature generation part, we read in like over 1.73 billion records. So I think it's around 30 gigabytes. And to do the data transformation and select the training data, and they overall just take like 6 minutes. And for training parts, you can see that it's also fairly fast. It's under 10 minutes to do those cross validations. And for the prediction, it's even faster. So we just read in the new data and to let the model to run and to make the predictions. So overall, this job is able to run daily on the production, even though right now it's part of other pipelines. So our current schedule is to run it every month. It's speed up the metadata discovery process from months to days. So previously we spent around 3 months to maybe can discover 11,000 new metadata. But right now we can just let model to do those predictions. Here are some example output. So basically, in the output, we also provide the probabilities so that other teams can also can rank and decide on which prediction they want to use based on different thresholds. And also, you can see that those newly discovered brands are not straightforward at all. You have to, for human reviewers, you would really have to do a lot of Google search to verify them. So to summarize, so we found that Spark is really good for data science applications. So it's much shortened the development cycle, and MLlab on top of it is very comprehensive, and it's very well integrated into a Spark. So you can just run it on your local machine, on your dev machine, and so the development and testing can be very, very efficient. And also, we've been using Scala to implement this project. So the code base is very small. It's only around 600 lines, so which is very easy to maintain. So in the future, I think we need a better understanding of those machine learning algorithms, how they are implemented in MLlab, so that we can know how to better optimize our setups. And so here I would like to thank our team, and with that I'm going to stop and open for questions.
Any questions? There's got to be one question somewhere. Okay.
Hey, thanks. So just to better understand sort of the business use case of your predictions, so you take these predictions of whether a keyword is a brand or not, and you use that and populate sort of like a graph metadata store that you use to infer those relationships. Is that stored sort of as like a ground truth? So I get that prediction is like 80%, that's good enough. So anything that's 80%, that's definitely a brand, insert it, or do you still sort of maintain that probability in your metadata store?
Yeah, so actually we have this quality check before we really load them into the repository. So we have threshold as 90%. So you basically, when we do quality check, we sample the part of the predictions and send them to the reviewers to review. It has to pass 90% precision, and so that we can import them. So there is such a step. So we're not importing everything. Yeah.
Well, once it's imported, it's there forever.
Yeah, it's there. But our repository have the editorial tools. So if the other users found it's incorrect, they are able to actually modify them. Yeah.
Hi. Thanks for the talk. How do you deal with minor variations in the brand? So some of them sometimes will have a copyright symbol, or they're spelled slightly different. So do you then have some kind of prefabricated ontology to kind of convert these variations to a root form?
Yeah, that's a great question. So we actually have this step. So we have we call them Synonym List. So basically, if these brand some brand they have different form, like Ralph Lauren has space or without space, or just RL. So we have such a mapping files, but it's actually not perfect. We're still in the process to updating them. But yeah, we need that. Otherwise, there are a lot of very sparse data. Yeah.
You mentioned you use Spark to develop and test your model. Yep. So I wonder when you finish that, when you're ready for production, how do you integrate that? How do you work with your tech team? Do you use the same code, or do they have another set of code? And how do they use your model? Do you persist your model and just hand it over to your tech? I'm just curious about how do you kind of integrate the data science work with the production work.
Yeah. So actually, in this project, we are the people who do the research and do those prototype development as well as push to production. So we don't have this type of communication going on. And for the Spark development, initially we actually developed the Python version to test our hypothesis. But we found that since Spark can be run locally, so as long as your data size is not big, so you can basically just use a Spark MLab, run your even laptop to do the experiments. So for ship to production, basically there's no much modifications. We just run them and test locally and basically just deploy the jar to the production. Yeah. Sorry.
You send say feature generation code and.
Yes.
Okay.
Yeah, but we actually also do the quality check after we deploy to production to make sure, they have the same behavior. Yeah.
Hi, thanks for the talk. But I have a question about on the front end. Did you have all the data you needed in HDFS? Wasn't it a challenge to get all the things stitched together in one place so you could run your thing? That's oftentimes one of the major challenges I face in my work. Can you talk a little bit about that?
So you mean how I gather the data, right? So actually, we have this pipeline to basically periodically. Right now, it's twice a week to generate read all those item specifics from our data warehouse. So that's how we keep refreshing our candidates. And after we get all those candidates, we also have the pipeline to gather all the supply and demand signal, the title occurrence, unique seller counts associated with all those item specifics. So that's how we aggregate the data. You guys write that yourself as the data science team? Yeah, we actually wrote them ourselves.
Hi. In one of your slides, you had a comparison between scikit and MLlib. I think it was accuracy. Did you use the same data set, or how does? Okay.
Yes. We found that it seems like MLlib is still a little bit lower. But
so when you do that comparison, you can't really use scikit on production level. So do you even?
No, we just compare it with different versions.
Okay.
Yeah, because we initially use scikit to do the prototype, so we just also output the performance to compare it with MLlib's behavior.
Okay.
Yeah.
Hi. So just to kind of piggyback off that question, I was curious about your setup. I think you did some comparisons relating to performance and I guess when you weren't using Spark. So I just wanted to know, what does the cluster look like, or how many nodes are you using? And then sort of slightly on a different note, going back to the question about probabilities, and brands, what exactly happens, I guess, when I just felt like I wasn't sure what the reasoning was, when you say, okay, the probability is over 0.9, do you then just start listing that brand? Is it just a new brand you're trying to adopt and see if if it will sell good on eBay, something like that?
Yep, so the first question, about the settings of the environments, we actually, I think, our cluster has tens of thousands of nodes, but here we only use a couple hundreds of them for this machine learning application.
What were you using before Spark?
Before Spark, actually, there are a lot of different ways. Depends on what your model is. So if you're using deep learning, we really basically train them on GPU machine and upload those matrix to the production and write those matrix multiplication parts in the production to do the computation. And if you are using logistic regression, so we have those APIs in production as a service, so we can directly use them. And for others, like other GBMs, so some teams have their own implementations. You really have to dig into their code base to try to reuse those. So it really depends on which model you're using. For the graduation part, so basically if we generate those graduate candidates and they are input into our repositories, yes, they will be reflected on the eBay website. So if you do a search and your records items are in those specific categories, then those predict, for example, new brands will be reflected on the left-hand side. Yeah, but still, it will still need to pass some editorial criteria, I believe. Yeah.
So after your execution, you will if the result is passing 90% of your score, then you will send to the user to do the review. And the user will do some decision, may accept or reject the result. And how do you incorporate that user decision into the next run?
That's a great question. So right now, we haven't really incorporated them because it's this project just finished. So in the future, for those user review results, we still want to incorporate those decisions into next round of training. But actually, for this evaluation purpose, we basically just sample a small set of the data and send them to the reviewers. So I just want to make sure that the precision is correct. Yeah, but the amount of data may not be that large, but it's still useful to add their decisions back to the training data. Yeah, we are thinking about having this feedback loop to add them to the production. Yeah.
So on the probabilities that you've shown, all of them are under 90%. Do you generate a confidence interval? And if they're under 90%, do you then choose a subset where you can't get over 90% and actually make a prediction as to identification of a brand?
Right now, yeah, we don't have confidence interval computed. Yeah, but yeah, that's a great suggestion, actually. We should think about that.
Cool, last question.
Hi, I have a question about your model. So when you test your model, are you assigning, for any new listing, are you assigning probability for each token? Or your model extracts some phrase and then assign probability?
Could you?
So you have a new listing, right?
Yeah.
You try to identify some metadata. So are you assigning a probability to each token, to each word?
No, just for item specifics.
For item?
Item specifics. So basically, the ones that when you list, you're asked to input those things, right? Input those aspects. So we basically, our model basically collect those item specifics from users' inputs and use classifier to classify whether this is a valid brand or valid model.
Okay.
Yeah.
Awesome. Well, we're about out of time for this presentation, but let's give Ching another round of applause.
Thank you.